Good evening. Mid-June 2023. Where we left off was reading about the complex numbers from this book, Functions of a Complex Variable. It's funny that these textbooks, are pocket-sized editions. Originally a few dollars. Oh, this price was 7/6 net, so that'd be like £1 6 pence, or £7 6 pence, or something like that, I suppose. Which is a sum. It's a tidy sum. I presupposed the knowledge of real variable theory corresponding approximately to the content of my course of analysis, Cambridge, 2nd edition, 1939. This is the author, Phillips. So, what I'm trying to understand is basically the Gaussian analysis and its conventions and its stipulations and its expectations and analyticity, which is the property of being analytic in a region or analytical in character, that is a little bit overloaded, where the field, the practice, the action is the computation of forms symbolically that result in computations of quantities numerically that result in computations of solutions to problems. And there was described the arithmetic of the complex numbers that make them as a field, and there was described some considerations of alternatives in terms of the definitions of the operations about basically multiplication of complex numbers. In other forms which would still see that the distributive law holds, thus making it as yet a field. And there was a discussion about the proof from algebra that the reals are unique up to isomorphism of the complete ordered field, and as to whether then that would mean that there would be an isomorphism among these terms in complex products in the complex plane, what would still establish that or not. In terms of topologies of all sorts, and topologies particularly that preserve order vis-a-vis topologies that only more or less establish character, there's to be made a discernment of the discernibility of the differences between a topology which establishes particular properties of the analytical character vis-a-vis topologies which are digital or otherwise in the space of functions by the pairwise, but not in terms of the sortes or the heap and transfer principle, and so. There is discussed division by zero and the roots after the roots of unity, and for example, the introduction of the imaginary number, the root of -1, or any of the roots of unity, or any of the roots of -1. I is not the only root of unity. There's one itself. That is in all sorts of roots of unity, being that multiplicative identity, 1 to any power is itself, and then there's all sorts of for any point on the unit circle, there's any number of roots in the complex that go to it, and then for any of the values 0, 1, or 1, 0, or 0, -1, or -1, 0, on the axes, then those particularly have, without even defining the rest of the complex plane, they just establish a lattice and have that those roots about would have to be that circle about that. Could be any other notion of the carriage of what maintains the properties of a rotation, but there only exist things on the lattice. There are lots of different ways to look at it, vis-a-vis that it's just the root of -1. And at the same time, it's still so that that's singular in this case, and makes it so that it closes out the field with that as this definition. And the author makes pretty clear that it's like division by zero is undefined, or meaningless, as he puts it. But when we say undefined, it's not the same thing as meaningless, because any expression in terms, in terms of it being well formed, otherwise in the terms, and it being excluded, is not so much meaningless as not having defined its meaning. It's undefined. And so then when we talk about indeterminate quantities, that's a gentler way of saying it doesn't exist. And undefined is a gentler way of saying then it doesn't exist. And meaningless is a little bit stronger way of saying it doesn't exist, now don't go there. Like so. So, continuing on page 3, the abbreviated notation is customary to denote a complex number whose imaginary part is 0 by the real number symbol x. If we adopt this practice, it is essential to realize that x may have two meanings: 1, the real number x, and 2, the complex number x, 0. Although in practice it is important to distinguish between 1 and 2, in practice it is although in theory it is important to distinguish between 1 and 2, in practice it is legitimate to confuse them. And if we use the abbreviated notation, which x stands for x naught and y stands for y naught, then x plus y equals x, 0 plus y, 0 equals x plus y, 0, and xy equals x, 0 dot y, 0 equals x dot y minus 0 dot 0, comma x dot 0 plus 0 dot y equals xy, 0. Now when it says to confuse them, to equate them, it's that they're different objects. They're different domains of objects, and there's two ways to look at the numbers. One is that the entire superset, or the largest set that contains, according to the real values or complex values so defined, the numbers embedded in them, the rationals, for example, the field for the complete order field, the integers, the elements of the lattice, integer lattice, that those are a subset of these ones. To say that they're so confused is only in terms of that their operations about them that carry them together, and the same things, the tensorial products, as it were, are either defined or undefined. And if they only have unique values, then it's fair to say that it's not confusing to say that they're so embedded in the space of each other, and then that particular theorems only apropos to those apply only to those. Of course, the usual way to build these things is from very simple notions, what kind of build the simpler parts of the numbers first, and then get up into these numbers with multiple scalars and their tuples, and these complex numbers, what would be matrix valued quantities, any other kinds of quantities that arise up above this number field, have various ways to look at it. And so, indeed, formally, it would usually be said that there are different kinds of things. And then the notion of relating that 1.0 equals 1 over 1 equals 1 in their value is in the real value space, and it has, that is variously so about that kind of thing. One way to look at that, how that gets into the non-standards, for example, this Dirichlet checkerboard bit, which is the idea of having a checkerboard, filling the integer lattice as by a checkerboard, where any square is either black or white, and all its neighboring squares above and below and to left and right are the opposite color. And then the idea is that shrinking that down to a unit interval would make a function that's everywhere discontinuous, or a domain that's everywhere discontinuous, that is 1 at these black squares and 0 at these white squares, or vice versa. This is a kind of thing that makes an example then for the relation of that to the embedding and the values in the spaces, is that because it was shrunk down by its ends to make that into 0, 1, it's only 0 and 1 that relate, that are in the same space of values in the embedding, and everything else about them and their properties has to be dealt with as its own, and has how it so interfaces with that. So that gets into what's called quasi-invariance, or Poincaré's plane, Dirichlet function. Here the signal continuity in the example, Or, for example, the line continuity or the Aristotle's continuum with respect to the field continuity. Mathematics has a very obvious missing thing, what is continuity when it's defined. The completeness that makes it so that you can define a domain as continuous, and that, for example, a point set is a line, to confuse them, as the author puts it, but more so to establish the results of extensionality, that they're equals under all the theorems of relevance and interest. So there's much to be said for it, and it's a key thing of this complementary duals, that going from both ways is to establish that this intentionality the one way meets in the middle of the nowhere, is extensionality the other way. And that's all the basic differences between intentionality and extensionality, is that intentionality is for a domain of objects solely defined by all their own definitions and solely restricted to only those theorems that apply to them, and also in the complement of all the things that don't apply to them, making so that intentionally there's only one such structure that makes it so unique that you can say that they're equals. In all models, they're equal. Has that then in all the relations are also equal. That the extensionality is where that's carried away, and so you still say equals. That's something you've computed by algebra that's a rational number, and something that you've computed by an infinite series or sum, like a geometric series or one of Zeno's products. Those are extensionally equal, even though they're formed of basically fundamentally different aspects of the number system of this whole number field, which is real valued, and then up in the infinite dimensional real value spaces, and then how that's attached variously to things like the complex numbers, courtesy and interpretation of what is the imaginary numbers and the roots of negative numbers. In this context, then, this notion of the identity dimension being built up about x equals y and living only in the first quadrant and only in positive numbers is just another example of a way to look at that, and then the way to look at that in terms of the integer lattice and the complete ordered field, and what results, how that things are defined in terms of that have the same content analytically as in that one octant of the quadrant, and how that makes it so to be able to build that out to the half plane, and otherwise when one or the other of the variables has a complement. These are the kinds of things that make it possible to look at the origami shape, which is an art of folding paper, usually square pieces of paper, and often according to very well-known and described patterns, into forms and shapes that look like structures. Three-dimensional structures like the crane or the turtle, or various things that are made with what's called origami. And so the idea of the way that these reflections and rotations occur about the affine and geometry, which preserves the things in these spaces, then gets into why that there are things like when there's discussed other kinds of geometries, like that on a disk there's this kind of Riemannian geometry, or there's Lobachevsky, or dot dot dot. Vis-a-vis Euclid's geometry, which is most regular in a sense, the most natural geometry. Although there's a notion in that a geometry of perspective is a thing, and the Mercator projections, how the globe is placed and displayed as an image, how it can be peeled as an orange and put back on the globe, and these kinds of things. All these kinds of projections in perspective, and about the folding and the unfolding, and the results make the same traces of the relations match after the folds, are all these matters of intentionality and extensionality, what result then for these singularities and multiplicities, and for these extensions and embeddings, how it's built up in this world of complementary duals that reflect on each other and complete each other. And then as to how they meet in the middle of nowhere, that's real analysis about the infinite. That is standardly established in various cases with things that largely are based on the ubiquitous success of Descartes and the Cartesian, about the origin as a singularity. in terms of other number systems, for example, that have division by 0. Results in infinity, because they're built between 0 and infinity, not from 0 out to infinity. So anyways, although in theory it is important to distinguish between the real number and the complex number, in practice it is legitimate to confuse them, and if we use the abbreviated notation in which x stands for x0, same. Hence, so far as sums and products are concerned, complex numbers whose imaginary parts are 0 can be treated as though they were real numbers. It is customary to denote the complex number 0, 1 by I. With this convention, I squared equals 0, 1 dot 0, 1 equals negative 1, 0, so that I may be regarded as the square root of the real number negative 1. Using the abbreviated notation, it follows that x, y equals x plus y iy. For since I equals 0, 1, we have that x plus iy equals x, 0 plus 0, 1 dot y, 0 equals x, 0 plus 0 dot y minus 1 dot 0, 0 dot 0 plus 1 dot y equals x, 0 plus 0, y equals x plus 0, 0, y equals x, y. Now, as regards to why he repeated the last term there, it's because he treated the addition of the two complex numbers as one complex number, and the addition carried in equals xy. By virtue of this relation, we see that in any operation involving sums and products, it is allowable to treat xy and I as though they were ordinary real numbers, with the proviso that I squared must always be replaced by negative 1. There are other roots of unity than negative 1, for that negative 1 squared is 1, is to be considered. Conjugate complex numbers. The conjugate complex numbers have the result as the real part. If z equals x plus iy, it is customary to write x equals rz, y equals iz. The arguments of it is the number x minus iy is said to be conjugate to z and is usually denoted by z tilde. It readily follows that the numbers conjugate to z1 plus z2 are z1, z2, and z1, z2 are z tilde 1 and z tilde 2 and z tilde 1, z tilde 2 respectively. Proofs of theorems on complex numbers are often considerably simplified by the use of conjugate complex numbers in virtue of the relations easily proved. The magnitude or modulus or arg z squared equals z tilde. 2rz equals z plus z tilde, and 2iz equals z minus z tilde. Now these are quite remarkable in the sense that the conjugates make these pairs, and so they establish all these relations as about it. And when we were talking about the identity dimension, it's kind of like an identity dimension about where the conjugates live, and so we can kind of talk about the notion of things on curves symmetrical about the identity dimension as conjugates on either side. Where at the same time it can also be considered to make a reflection of those, because it has a boundary on the far side, that those are also like so, but it could be that their products either fall to the identity dimension or fall to either axis. Here there's a difference between x plus yi and x minus yi is largely determined from the fact that minus I squared equals 1, and there's no imaginary term left in it. And so this relation then that 2 are the real part of z is the sum of the number and conjugate, and the 2i, iz is the difference. That gets into these, again, for this kind of poster board about the identity dimension, those are addition formula, and making for what's computed as a product in terms of one thing according to a given particular kind of thing, in terms of not where, and like in the logarithmic, it ends up you can just sum up the exponents to compute the product, is that you can compute the doubling of the magnitude of one of these things by its sum. That not being very unusual, where in the algebra that multiplication is repeated addition, and it's 2x equals x plus x. But as we discussed here before somewhat at length, there's differences in arithmetics that are kind of built up the usual way with addition and multiplication, and thanks to Peano, because Giuseppe Peano invented some axioms that kind of make it clear. And then there's Peano and Pressburger about where addition and multiplication are first and second order, because Peano has first and second order and Pressburger has it first order, the operation. Then the other notion that's discussed here is that, well, there's addition, and that, well, there's increment, and it makes up addition, and it makes up multiplication, and it makes up powers. And then there's division, and it makes up parts, and it makes up infinitesimals, vis-a-vis how it makes up its complement, multiplication, and vis-a-vis how addition makes up its complement and subtraction. And the idea, it ends up kind of like either a long subtraction or a long multiplication. What does that mean? Well, when we implement our systems of numbers and define addition, then subtraction, or addition and multiplication, as was just mentioned in the naturals, and then make that a reflection principle about that, and call it the same thing as a group. We can fuse the group, the numbers, and call it a group, after otherwise equipping the elements with operations, or demonstrating that the operations exist and are closed and are like so, without necessarily the group's operations, but the parts of it, that then it would be a model of a group, and vice versa, and a model of a ring for the rationals or so, or the integers embedded, or the model of the field, ... That then what ends up kind of getting defined last is the long way, in terms of how it has to be modeled as the completion of these other things, or that it has to go outside the realm to make up the new things. Because with the addition and division, having multiplication doesn't really add new elements to it. It's closed to addition and multiplication. When you add division, then it splits all what are otherwise integers into rationals. And so the idea is that, well, if there's addition and the increment on the one side, and about how it would be so, then about how that would just make an example of the deconstructive account of models of arithmetic that are like so, where an addition formula is not necessarily the same thing as the multiplication, so that the properties of these numbers as conjugates, and having these sorts of magnitudes declared so about them, would build up for these different aspects of the arithmetic, either way, why these are addition formula and not just trivial. The author goes on, to prove that the modulus magnitude of the product of two complex numbers is the product of their magnitudes, or moduli, we proceed as follows. And he expands z1, z2, their product squared, and writes out z1, z2, z tilde 1, z tilde 2 equals z tilde z1, z tilde 1 dot z2, z tilde 2 equals magnitude of z1 squared dot magnitude of z2 squared. And so, since the modulus of a complex number is never negative, z1, z2 equals z1 dot z2. So what he's done is he's employed the properties of these conjugates to establish the properties of the dot product of the magnitudes. That's something to figure out a little bit more. Why is it necessary that it's so defined that way? Why is it necessary that it employ the property that the complex number is negative or negative to establish that there is no alternative? These are the kinds of questions that get into the derivational context. That in this descriptive differential dynamics, these are the descriptive in the definitions, and the dynamics in the definitions. He reads the theorem: the modulus of the sum of two complex numbers cannot exceed the sum of their moduli. This is kind of known usually as triangle rule, or Cauchy-Schwarz inequality, in terms of elements of a vector space. It establishes an inequality that the magnitude of the sum is less than or equal to the sum of the magnitudes. A result which can be readily extended by induction to any finite number of complex numbers. In a similar way, and in members of a vector space, in a similar way, we can prove another useful result vis-a-vis, or videlicet. Viz is, it means, as for example. So you sometimes, rarely you'd ever see for x, or but for example, but you see viz, and it means videlicet, and it means, for example. C. Magnitude of z1 minus z2 is greater than or equal to the magnitude of z1 minus the magnitude of z2. And he says we have magnitude of z1 minus z2 squared equals magnitude of z1 squared minus 2r, employing this identity in the conjugates. Minus 2r, z1, z tilde 2, plus magnitude of z2 squared. Now that he's replaced z, he's kind of added z plus z tilde in the middle there. It's just factoring out the products here, multiplying out the products. It's greater than or equal to z1 bracket magnitude of z1 squared minus 2 magnitude z1 z tilde 2 plus magnitude of z2 squared equals this quantity squared, magnitude of z1 minus magnitude of z2. Hence, magnitude of z1 minus z2 is greater than or equal to the magnitude of this quantity, magnitude of z1 minus the magnitude of z2. So what's to be taken from this section is essentially this, that according to the properties of the existence of the conjugate numbers, when there are any of these things that otherwise have to do, and then there's tuples, and there's pairwise multiplication of the things, and the products in the center, or what keep in or keep out, that the existence of the properties of these conjugates and so on, and how after this special case for -1 means that what's reflected as a quantity in the one flips back and forth in the quantity in the other one, is about this notion of how -1 in the conjugates only serves to flip the term from one side to the other side, or to result for the term that either it accumulates on the one side and the other side. So now in our identity dimension example, what we have in mind, it might be that there would be similarly this idea of an alternation in terms of well, is it in the upper or the lower of the quadrant? Is it above or below the identity line x equals y? And where it is so, then that makes for when they're multiplied together and there's some aspect basically in the upper or lower, kind of like here real and imaginary, but upper or lower, and there's anything that's defined that makes a product that carries one or the other, then it can be established to be these simple properties of complex numbers to make a simpler imaginary numbers. Notions. integument. These identity dimension numbers. So that's what makes for a property of the deconstructive account, to get out for what is the sensible and fungible tractable, to reduce to that's what in terms makes for these derivations, so that later when these properties are used of these elements of the complex number plane as if they're members of a vector space, then it's made so that this is detachable. And then how it goes about is particularly is how to make it so for other models of other spaces with similar type properties, to make them so that it works out then for matters of projective and perspective, where it's pretty much that in matters of projective and perspective, there's two things. One is that there's a point at infinity where there's the receding line in the middle. And the other is that the field of vision is less than 180 degrees. It's in front of the plane. When we think about the light cone, it's instead kind of like what's in front of us. But all the way on the peripheral is still visible vis-a-vis the matters of projective and perspective. So in this identity dimension, then in the quadrant, and then each octant of that, there's a notion of the perspective down the line of identity. And it would be similarly so when you think about just in the real plane and or in 3 dimensions, that there's just forward, that there's this notion of the peripheral and the parallel, to make for parallax, and which is the notion that via stereoscopic vision you can determine the distance of something in its perspective by moving the origin back and forth, and virial theorems and this kind of thing, and the peripheral parallax, which is what vanishes on the sides, or what establishes on the sides and comes into vision fully from where at the edge of perspective and projection it's vanishing. That there's the vanishing of projection and perspective in the infinite and to the left and right. So, section 3 here says geometrical representation of complex numbers. If we denote x squared plus y squared quantity to the 1/2, or the root of x squared plus y squared, by r, so kind of like it says by Pythagoras's theorem establishing the hypotenuse and to the triangle so established, and above the ordinate what it falls to, about the abscissa that it connects to or falls from, and choose theta, so that r cosine theta equals x and r sine theta equals y. Now you can see how this is built from the Pythagorean theorem and the definition of cosine and sine and hypotenuse, or tangent, the function. Then r and theta are clearly the radius vector and vectorial angle of the point P, x comma y, referred to an origin 0 and rectangular axes 0x comma 0y. Now what's interesting is notation, how he writes this. So when he says referred to an origin, then we're talking about the abscissa and the ordinates, and what that means when it's a matter of projective space where something lives and fits and sits, that when you draw otherwise this plane thing that's a free creation and construction geometry, that's it's referred to an origin y, because otherwise you might otherwise say that it's referenced by an origin. The origin and its orthonormal vector basis is what holds this thing together. That's all our simple notions of linear algebra and the usual original analysis. So it's interesting that he writes it this way. Maybe it's just a Briticism. And rectangular axes 0x, 0y. It is clear that any complex number can be represented geometrically by the point P, whose Cartesian coordinates are x comma y, or whose polar coordinates are r comma theta. And the representation of complex numbers thus afforded is called the Argand diagram. So here there's this discussion of Argand and Wessel, and the notion that Argand is named in applications on the complex plane, and that Argand was one of the first to make applications of the complex analysis about the plane and the geometry and stuff like that. That this is then the Argand diagram, and then the Wessel diagram is using the same numbers and the same objects of geometry, and it's not too different, but it's used in different contexts about different applications about other extensions, other things. So it just represents an analysis, Argand style analysis, Wessel style analysis about the Eulerian or Euler's. People say, "Oh, did you know Euler's name is pronounced Euler?" I'm like, "Oh yeah, sure." Also, it's spelled kind of like Euler, or Euler, but anyways, it's meant Euler or Euler, and the Gaussian style, complex analysis. There are others. By the definition already given, it is evident that R is the modulus, or the magnitude, of Z equals x comma y, the complex number. The angle theta is called the argument of Z. Written theta equals arg Z. All right, well, I was thinking the argument was, the argument of Z. There's use of the word argument in term and function theory, and so it's not to be confused. But here it's theta is arg Z, and throughout most that applications of complex theory where it doesn't get into the logic, where there's discussion in terms of the functions, what is called the argument, it's particular in this context. And it's just spelled out like a little word, ARG, arg Z. The argument is not unique, for if theta be a value of the argument, so also is 2n pi plus theta, where n is an integer. And so that basically means theta plus a full rotation, 360 degrees, or 2 pi, any number of times. You might call that a winding number. Is the number is how many times it winds around is the winding number. That's just the usual notion. It's the same thing as polar coordinates in the real plane, r squared. That the angle is non-unique in the coordinates. Now, how is that similar in a square or something like that compared to a circle in the polar coordinates, and a square having this non-unique things? It's like, well, it's not unique if you consider symmetry is about positive and negative and even and odd, not unique, but in the Cartesian, it's just kind of rendered out. That the notion of the integer lattice squares, connected squares, and circles from the origin is defining the same thing, is about the most usual coordinate substitution, transformation of coordinates, different coordinate settings, and that the rules are so well established as by Pythagoras that the identities that rise from trigonometric functions carry on up. So here are a couple things we talk about, or I talk about, are the n-gonometric, and that being about that the sine and cosine, besides Pythagoras' theorem about the right triangles, is also results from equilateral triangles. They get unrolled and re-roll back up, and unrolled and re-roll back up, and that then the spiral space-filling curve is that's the most natural continuum. It's kind of like drawing the line segment from 0 to 1 already and making the Cartesian coordinates this way. Is that the Cartesian coordinates live according to this natural spiral space-filling curve continuum. That's how things are. let P1 and P2 be the points Z1 and Z2, then we can represent an addition in the following way. Through P1, draw P1, P3 equal to and parallel to OP2. So the line connecting so what it does is it assigns these points P1 and P2 and P3, or this rectangle is drawn with one corner at the origin and the other one with its first leg up to P1. Then that's the one that's our theta is that coordinate. That the other one's point is next one is called P2, and then P3 is the opposite from the origin, if that's the same diagram here. And through P1, draw P1, P3 equal to and parallel to OP2. Well, that's just that the opposite sides of the rectangle are equal. Then P3 has coordinates x1 plus x2, y1 plus y2, and so P3 represents the point z1 plus z2. So this is usual properties of the vector space. He says in vectorial notation, and when we write vectors in the vector analysis in the vector space, and when those are the objects, we usually just each vector will just have a name as a variable name, because it's just the vector in whatever space it lives in. And as an element in the member of the vector space, it has the vector product of various kinds to be defined. It has the inner product and outer products, and these things have been defined quite a ways back in the talks. As now, since the past few months, I've recorded like 60 or more hours of these talks in mathematics. But somewhere in there is quite a big long discussion about the vector space and the inner and outer products and the methods and analysis, and that it ends up being just like this conversation started about the complementary duals, and the very notion that the whole understanding of the number system and the number field involves looking at it both ways. In the vectorial notation here of the author, what he's done is he's written lines like you write lines from geometry, which is 2 points that connect them, like O for the origin and P1 or P3 here, and then a bar over them. Where oftentimes when you write it, when your vectors are so ubiquitous in linear analyses these days, and also they live in the world of scalars too, that they're just written the variables, or they're written the variables in boldface, or they're written the variables in boldface with a little arrow over them. And to the right, and then but otherwise he just has a bar over these. So he says the vector OP3 equals the vector OP1 plus the vector P1 P3 equals the vector OP1 plus vector OP2 equals the vector OP2 plus vector P2 P3. Similarly, if we have P3 is the point Z3, Z3 minus Z2 equals the vector of OP3 minus the vector of OP2 equals the vector of OP3 plus the vector of P3 P1 equals vector OP1 equals Z1. So that the vector field is kind of like so. He'll kind of have left out the discussion about the confusion of the numbers and spaces and all around, vis-a-vis how he attaches this to the models of the elements of a vector space, vis-a-vis the models of and elements of the complex planed Argand's diagram, the geometrical interpretation including polar coordinates. Though long-winded, it ends up becoming much more brief when it's understood that it stands up on at least 2 legs. It is convenient to write CIS theta for cosine theta plus I sine theta. If Z1 equals R1 CIS theta 1, Z2 equals R2 CIS theta 2, ... Zn equals R sub n CIS theta n, then by de Moivre's theorem, now this I really will have to review. This will be the fundamental thing that it does all the completion and stuff that in this extensions and analyticity in this. Z1 Z2 ... Zn equals R1 R2 ... Rn, and CIS of this product, theta 1 plus theta 2 plus dot 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 theta n. So this is an addition formula, and it helps relate the product of all these complex numbers by the product of the radiuses. R is for radius in polar coordinates, and but it was also the magnitude and the moduli of the complex number times cosine theta plus I sine theta of theta 1 plus theta 2 plus dot dot dot. So he mentions de Moivre, and I'll be looking at that particularly as an addition formula, and it makes use of the cosine and sine theta because they are the most handy trigonometric functions around, and they're very handy, and they have a lot of their identities are known, and they have a lot of identities. So by being so, they're pretty central mathematical objects, but there are others. And so what I'll be looking to is generalizations of de Moivre's theorem about addition formula about these kind of objects, because in this identity dimension, and as we've been talking about how to establish for the identity dimension, is something like the conjugates are reflecting some of these ideas about the symmetries above and below the identity dimension line in this quadrant, flipping back and forth between x and y. This kind of analysis then in terms of coordinates in that in the polar, and coordinates in that in the radial from any of the points on the line, kind of sweeping from the origin across and up the line. When you think of like a lighthouse, and it spins around, and then so as it spins around in the distance, and you can kind of see it going all the way around and flies all around the area around it. But then when it crosses your own vision, it just flashes brightly, for example. The idea being that in matters of projection and perspective is that there is more than one spot in this identity dimension for these things to sit on the lattice points out the axes in terms of the relation to the identity dimension, the line segment. So these are the kinds of things that are a result of abstraction and always turning things over in the mind, so that it results that kind of deliberation makes it so that then it's because it's sensible and it's fungible, because the terms are general enough and reciprocal enough and reflective enough, there's the inverses exist, that is tractable, that this turning things over results, then it settles out what is necessary, what is a form, and also what is possible, what's projective. So kind of figuring out the perspective and projective or any of these other notions of complementary duals in this way, in abstraction. It's critical thinking. One way to look at it is this higher order, but it's not necessarily so. It's as well lower order. It's the deductive analysis is not just closures for the process of elimination, which is closures in deductive analysis, but on the outside of that there are none, that completions live outside of that. So that's kind of a digression about analytical properties and methods and analysis. But here's for de Moivre's theorem that there's an addition formula for these complex numbers, and it's been built only so much from these properties of the arithmetic itself and the arithmetical laws of associativity and commutativity and distributivity and transitivity, and then the notion of the establishment and the observation that the conjugates have these properties, and that for them then these other products stand up and work out and make up for a norm in the plane, like so. Whereas it's not so dissimilar in the vector space and the real vector space, but the complex numbers just kind of stand up having it like that. So if you don't already have a vector space, you can still get the same metric or Furner norm and the distance. Then there's here that this kind of association with the vector space results computation in the in a model of the vector space from the geometric attachment to points in its plane, which is like, well, what's a rectangle that has numbers attached to imaginary numbers? Well, you just think of it like R2, and then you just compute things on it, and then you use it to compute lengths. The magnitude is still the same. Well, can I do that just to compute anything? It's like, well, no, don't do that. But what you can is you know, it's up to you to determine that after computing how it works out both ways, that it's good both ways. Or when it's good only one way, that all the terms that arise from it are put back down. There are various ways to make closure and deductive closure. So clearly I'm very excited about de Moivre's theorem and cosine theta plus I sine theta. Which readily exhibits the fact that the modulus or magnitude and argument of a product are equal respectively to the product, the moduli, and the sum of the arguments of the factors. An addition formula and a summation formula. In particular, if n be a positive integer and z equals r cis theta, z to the n equals r to the n cis n theta. For an integer, a positive integer, where that's making it so how these things are going to be interesting about when those extended beyond those or not exist for those. And in these other terms of the spaces in the number fields, which readily exhibits the fact. In particular, if n be a positive integer and z equals r cosine, r times the quantity cosine theta plus I sine theta, z to the n equals r to the n times the quantity cosine n theta plus I sine n theta. Well, now that's interesting because it's not in terms of this gets into there's a discussion about what is the rotation. Is it turning all the way around, meaning facing the other way, or is it turning completely around and facing the original direction? What is a rotation? And then there's also like, what is a turn? Is it a 90-degree turn, or does a 45-degree turn suffice? Now, the notion, because otherwise there's a notion that why is 2 pi radians a thing? Can't it just be called like, why isn't pi 6.28 instead of 3.14? Well, because then it's derived, and a lot of things about the circle are would be in half instead. Well, it's called pi diameter, isn't it? And it's like, oh yeah, but there's something else to get figured out. Well, couldn't it just be pi 2r or something? Yeah, I suppose. Anyways, then the notions of what are these the multiples that these integers carry down in the fact that it's an addition formula and a summation formula for these integers is just what makes it possible to then keep it tractable. Once you have the existence of this addition formula, you can compute it and you can close it and you can figure out how to set it and put it in a can and bust it open. And it goes back in. But the point is that then I shouldn't digress too much because there's a linear development here. It needs to be read out. Similarly, Z1 over Z2. Now recall the particularly, in a sense, incongruous notion of division because it's possible to multiply two monomials, but their division always involves that the bottom monomial can be 0. So z1 over z2 equals r1 over r2 of CIS, this quantity, theta 1 minus theta 2. So then there's like and that's for being an identity. So any identity is not necessarily an addition formula. Any addition formula is an identity in a formula. But here, this formula and this identity is then has about the notions of the signs and particularly here what's with regards to arithmetic and the signs that carry back and forth these differences and products, and about the geometrical relations attached to the Argand diagram. That the complex plane is just complex numbers. The Argand diagram is attached to these vector products as if it were also r squared. And then using trigonometry about them to determine various things that are as rigid lengths fixed using linear algebra and geometry. If n is a positive integer, there are n distinct values of z to the 1 over n. So if n is a positive integer, there are n distinct values of z to the 1 over n. So n is the power of z to the n here. So the complex number taken to a particular power. So we take 1 to the power, then there are n distinct values of z to the 1. So 1 and 1 and 1. But we know that 1, the real number that has been just confused, has all the roots of unity, for example. How about 2? 1 squared, yeah, so for 1, you know, z to the 1 over n, like the square root of z is, there's 2 values for it, and so that makes sense when you get into thinking, well, yeah, there are 2 values for square root. It's the quadratic, there's roots, there's squares. You could write it out as a quadratic in powers and find the roots. How about 3? There, 1, 2, 3. Cube root of 1 is 1, and the nice thing also about the nth roots of unity about the circle is they're just equidistributed about the circle. So like the first one is always 1, and the other ones, if it's thirds, you just divide the circle into thirds, and that those points on the other sides are the third roots of unity. So the second roots are square roots of unity, or the cube roots of unity, the tesseract roots of unity. I forget what the fifth order square, square, cube, tesseract is called, but it gets into rows, columns, pillars, and files, and I rows when you talk about them as blocks, block matrix. If n is a positive integer, there are n distinct values of z to the 1 over n. If m is any integer, since CIS of this quantity, theta plus 2m pi over n, that quantity, to the power of n equals CIS theta, cosine theta plus I sine theta. This is an identity, and it's been introduced, and so kind of like the Moivre's theorem, I need to follow up on this other bit here. It follows that r to the 1 over n of cosine theta plus I sine theta of this quantity theta plus 2m pi over n is an nth root of z equals r CIS theta. If we substitute the numbers 0, 1, 2, n minus 1 in succession for m, we obtain n distinct values of z to the 1 over n, or the nth root of z. and the substitution of other integers for m merely gives rise to repetitions of these values. In this space, under these terms, not on the outside, or projected. Also, there can be no other values, since the nth root of z is a root of the equation u to the n equals z, which cannot have more than n roots. Yeah, that's the fundamental theorem of algebra of sorts. And there's a fundamental theorem of algebra and the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic of standard arithmetic, is that numbers have unique prime factorizations. And the fundamental theorem of algebra is that numbers have roots according to the order of the polynomial. Now, I'm not exactly sure if that's the fundamental theorem, but it's a pretty contrived kind of object that brings and carries around under this multiplicity or so on. Singularity theory is a multiplicity theory. Similarly, if p and q are integers prime to each other and q is positive, z of the qth root of z to the p equals the qth root of r to the p, or r to the p over q, times cis of this quantity p theta plus 2m pi, that quantity over q. Cis of that, where m equals 0, 1, dot, 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 2, dot, 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 to q minus 1. So that's about like ZP. ZP is a totally different thing. ZP is a fixed group of integers. It's finite. Finite rings and this and that. And they're particular about the primes and about how when you alternate through by the coprime numbers, that they'll fill in eventually the moduli of what otherwise makes them moduli that, according to moduli, that are not coprime to the size of the finite group, finite field. For the fields, that they would skip numbers that essentially they do, but that otherwise that's what gets in the way for the coprime values, that they collide or fill each other up. So rounding out or finishing up this section 3 by considering the modulus and argument of a complex number, the operation of multiplying any complex number x plus iy by I is easily seen to be equivalent to turning the line OP through a right angle in the positive counterclockwise sense. We have just seen that arg z1 z2 equals arg z1 plus arg z2, arg of this quantity z1 over z2 equals arg z1 minus arg z2, so that the formal process of taking arguments is similar to that of taking logarithms. It's about addition to subtraction formula. Hence, if arg x plus iy equals a, and arg I quantity x plus iy equals arg I plus arg quantity x plus iy equals 1/2 pi plus a, since root or magnitude of I equals 1, multiplying by I leaves this magnitude of x plus iy unaltered. Well, that's interesting, and it gets in the definitions of rotations and the meanings and stuff about 2 pi and radians. And radians are dimensionless units in this kind of thing. And well, that's something to be said about this identity dimension, but it's going to come in also that there's various notions about it in terms of the existence and the counts and the multiplicities of roots. And when, according to winding numbers or something like that, the rolling out, the crunching out, the grinding out these roots in an analog setting where the only way to compute them is the device that actually carries through the course of motion geometrically to get on out through all those. these are the kinds of things that go into making for models of y after deconstructive accounts. Then it's possible to look some more at these functions of a complex variable in the mathematics of a complex variable, as that there's going to be a lot of different paths and directions and routes chosen to employ various features that make them so tractable and similar as these and those and other things, and then relate them to these and those and other things in terms of linear algebra and vectors and real algebra and tensorial products and quantities and da. So I'm glad I'm refreshing a little bit on that, because it's going to advise me on all these other realms where the authors are free to say, oh, well, we're just going to work in complex numbers, or this function is defined in complex numbers, that it's going to be set up and tore down from that and taken apart and put back together, so that it becomes clear that part of the facility of working with higher level mathematics is the lower level mathematics, and vice versa, and getting either way, and that the familiarity gained is much conducive to the operation. Well, have a great day.